Mars is not genuinely red in hue. When we gaze at Mars, the red planet, it most surely appears red. Humans have been observing it since the dawn of time, and the Egyptians referred to it as the Red One. However, Mars is not genuinely red in hue. Yes, it appears red to us, and the surface also appears red due to the many types of ferric oxide found in Martian dust. However, the crimson color fades quickly if you get a close-up view of Mars with an orbiter or rover. It stops being red once you simply dig a few millimeters deeper. What could be the cause of that? In this video, let's speak about the motivation for that. We can all agree that Earth is a lovely world. From space, we can observe that the Earth has many different hues. Our sky is blue, and sometimes that color is a result of the atmosphere's preference for dispersing shorter wavelength blue light in all directions, which gives it its distinctive hue. But at sunset, light must traverse the atmosphere for a longer period of time. Longer wavelength yellow and red light is what humans see because blue light, which has a shorter wavelength, is scattered more widely as sunlight moves farther. Because water molecules absorb longer wavelength red light better than blue light, the oceans are also blue. While the ice tops and sky are always white, the continents seem brown or green depending on how much or little vegetation grows there. Red, however, is the most common color on Mars. The sky, despite being very thin, seems crimson, as does the Earth, the mountains, the lowlands, and the atmosphere. Red is present everywhere, including the mountains, sand dunes, and lowlands. The ice caps and clouds, which are visible from Earth but seem white with a faint reddish tint, are the only exceptions. Surprisingly, the red planet has a fairly shallow red hue. The redness disappears even if we only go a few millimeters below the surface. We must first comprehend why Mars seems red in order to comprehend why that is the case. The most noticeable aspect of the planet throughout all languages, civilizations, and historical periods has been its crimson. Mars is referred to as Mangala in Sanskrit, which also means crimson. Hardecker, its Egyptian name, simply translates as the Crimson One. As space technology has developed over time, we have captured images that unequivocally demonstrate that the atmosphere above Mars is fundamentally red. Blue light is scattered widely by Rayleigh scattering in the Earth's atmosphere, while red light is essentially untouched. However, the Rayleigh scattering from gas molecules in Mars' atmosphere only has a tiny impact because it is just 0.7% as thick as Earth's. Instead, there are presumably two ways that dust particles predominate in the Martian atmosphere. The increased absorption at the short optical wavelengths, which range from 400 to 600 nanometers, could be the primary factor. The second one results from the fact that larger dust particles, 3 microns or greater, scatter longer wavelength light from Rayleigh scattering more effectively than air gas particles do, which scatter shorter wavelength light. On Mars, you may study the suspended dust particles to learn a lot about how light is affected by it. This dust is quite similar to the iron-rich, highly reflective regions of Mars. Scientists were able to determine that nanocrystalline red hematite is the most common form of dust on Mars using the ESA's Mars Express mission's Omega tool. It has the right size and composition for the Martian winds since it is composed of incredibly small particles ranging in size from 3 to 40 microns. Large amounts of dust are constantly being swept into the air by the rapid Martian, where it remains rather evenly mixed even when there are no dust storms. The plot thickens as you begin to closely examine the Martian terrain. The surface features of Mars have been observed to vary over time ever since detailed observations began, first from circling spacecraft and then by landers and rovers. On Mars, there are parts that are brighter and darker, and the darker areas would change in a never-before-seen manner. They would appear dark at first, then cover them with dust from nearby lighter places before returning to being dark. Long before we noticed that the dark regions that changed all shared a few characteristics with the dark regions that remained the same, we were unsure of why. For example, the dark areas that altered through time had lower altitudes, steeper slopes, and were surrounded by lighter sections. On the other hand, the larger, more extensive, higher elevation, steeper slope black patches did not change over time. Carl Sagan identified the cause as follows: this fine, sand-like dust, which is spread around the surface of Mars by winds, covers the planet Mars. This sand gets blown around, but it likes to travel short distances, to travel from higher to lower elevations or to equivalent heights rather than up to much higher elevations, and to travel down steeper slopes as opposed to shallower slopes. In other words, Mars' predominant color is red dust, which is only apparent on the planet's surface. That's not really a poetic way of saying it, but most of the world is covered in a thin layer of dust, only a few millimeters thick. The dust is thought to be only 2 meters, 7 feet, thick even at the deepest area, the Tharsis region, which is made up of 3 incredibly large volcanoes scarcely offset from Olympus Mons, which appears to be to the plateau's northwest. If you were to examine this, would you see any similarities or differences between the topography and ferric oxide maps of Mars? However, before we answer that query, you need to be aware that ferric oxide doesn't always equate to red Mars dust. Everywhere on the planet, including the crust, lava flows, and Martian dust, is home to ferric oxide. As a result, while ferric oxides are present everywhere on Mars, their abundances are highest in the northern and mid-latitudes and lowest in the southern latitudes. This information is revealed when looking at a ferric oxide map of Mars, which was once again produced by the amazing Omega instrument aboard ESA's Mars Express. The topography of Mars shows that the elevation varies unusually across its surface, and that this variation is only loosely related to the existence of ferric oxides. Although the concentration of ferric oxides falls in the lowlands to the east, the highest heights are found in the ferric oxide-rich Tharsis region. Additionally, ferric oxide may exist on Mars in forms other than the red hematite. Magnetite, which is black in color, is another substance. We believe that there is a dazzling, globally scattered, globally uniform collection of dust that is swept up into and remains in the atmosphere. This has been our consistent belief for many years. The dust is largely suspended in the tenuous Martian atmosphere, and despite possible increases in concentration due to events like dust storms, it never reaches a negligibly low level. The dust that gives Mars' atmosphere its color is typically abundant, although the color of the surface of Mars varies greatly. The settling of air dust is merely one factor that affects the surface's color. Our landers and rovers have shown us that Mars does not have a consistent red hue. While many rocky items and deposits on the surface appear to be a variety of hues, including brown, golden, tan, and even greenish or yellow, depending on the minerals that make up those deposits, the surface is actually more of an orangey butterscotch tint overall. How red hematite particles are created is one topic that has to be answered. Erosion is a wholly physical process that can produce hematite. Part of the magnetite transforms into hematite when quartz powder, quartz sand, and quartz dust are combined and shaken in a flask. When quartz cracks, exposing oxygen atoms that link to the broken magnetite connections and generate hematite, a black combination dominated by magnetite, turns red. Perhaps the assertion that water is the cause of ferric oxides is a figurative red herring after all. Hematite is ultimately responsible for the red color of Mars. Even while ferric oxides are common, only hematite and the tiny dust particles floating in Mars' atmosphere are mostly responsible for the red color, which covers the first few millimeters of the planet's surface. You would assume Rayleigh scattering would triumph, turning the sky blue like they are on Earth, if we could somehow quiet the atmosphere for extended periods of time and wait for the Martian dust to settle. However, due to the fragile and thin Martian atmosphere, it would appear as though the sky was extremely gloomy, being almost totally black with a faint bluish tint. You could view certain stars and up to 6 planets, including Mercury, Venus, Earth, Jupiter, Saturn, and possibly Uranus, even during the day if you could successfully block out the brightness produced by the planet's surface. Mars is referred to as the red planet, but only a small portion of it is actually red. When we gaze at Mars' topmost layer, it seems red to us. What do you think of its color, then? Can you conceive of any other planets that could fool us in this way? Share the video with your friends and let us know what you think in the comments section down below.